Welcome to the Science of Ageless Living. I'm your host, Dr. Ethan Hausman-Marquis. Why do some people look and feel 10 years younger at 60, while others seem to age overnight? It's not just good genes, expensive creams, or pure luck. It's peptides, the tiny molecular messengers that your genes are constantly writing every single second of your life. Let me explain what a peptide actually is. Imagine a short chain made of 2 to 50 amino acids linked together like a tiny sentence written in the language of life. These short chains aren't just building blocks, they're smart signals. They act as repair crews, communication lines, hormone regulators, and command centers inside every one of your cells. Today, we're going on a complete journey, the full story most people never hear. We'll start at the very beginning, inside your DNA blueprint. Then we'll walk through the incredible cellular factory that reads those genes and builds these peptides. After that, we'll watch how these peptides travel through your body, knock on cell doors, and literally tell your cells what to do, when to repair, when to fight inflammation, when to grow, and when to clean house. And here's why this matters more than ever for staying biologically young. When your peptide pipeline runs smoothly, inflammation drops, damaged cells get repaired faster, collagen production stays high, energy levels remain strong, and your body actually slows down the aging process at the cellular level. But when that pipeline glitches because of stress, poor nutrition, toxins, or simply the passage of time repair slows, chronic inflammation rises, and the visible and invisible signs of aging show up. Wrinkles, sagging skin, constant fatigue, brain fog, and eventually higher risk of disease. The good news? Once you understand how this system really works, you gain powerful new ways to support it. So let's dive in. So the big question is, where do these powerful little peptides actually come from? The answer is written directly into your DNA. Every single peptide your body makes has its own genetic recipe stored in specific stretches of your genome. Think of your DNA as the ultimate master recipe book sitting in the library of every cell, and each peptide, it's a short, precise paragraph in that book, a set of instructions that tells the cell exactly which amino acids to link together and in what order. Here's how the code works. DNA is made of 4 letters, A, C, G, and T. These letters are read in groups of 3 called triplet codons. Each triplet is like a 3-letter word that spells out one specific amino acid. There are 20 possible amino acids the body uses, the 20 letters of the protein alphabet. With those building blocks, your cells can create an almost infinite variety of peptides and proteins. Now, not every gene codes for a finished peptide on its own. Some genes produce long, complex proteins. Think of them as the main dishes. But hidden inside those larger proteins are smaller signaling peptides that get clipped out later, like secret messages tucked into a bigger letter. Other genes make short peptides directly, tiny but incredibly powerful messengers. Here's where aging enters the picture. As we get older, our DNA itself doesn't usually change. The recipe book stays mostly the same. But the way we read that book does change dramatically. This is called epigenetics, the layer of chemical tags, like little methyl groups, that sit on top of the DNA. These tags can silence certain genes or crank others up too high. What does that mean for peptides? Over time, epigenetic changes can turn down the genes responsible for making collagen-boosting peptides, the ones that keep your skin firm and elastic. They can weaken the genes that produce immune-regulating peptides that fight infections and repair tissue. At the same time, they can overactivate genes that create pro-inflammatory peptides, turning up the volume on chronic low-grade inflammation, the kind that quietly accelerates aging. The result? Less repair, more damage, slower recovery, and the gradual appearance of wrinkles, joint stiffness, fatigue, and other classic signs of getting older. But here's the empowering takeaway I want you to remember. Your genes don't fundamentally change as you age, but how they're read absolutely does. And that's exactly where longevity lives, in learning how to influence the reading process so your peptide production stays youthful and balanced for decades longer. So the recipe exists in your DNA, beautifully written and waiting. Now the question becomes, how does the cell actually cook it? How does it turn that genetic paragraph into a real working peptide molecule? Let's step into the cellular kitchen and find out. So we've seen that the recipes for peptides are written into your DNA. Now the real magic begins. How does the cell actually turn those recipes into real molecules? And more importantly, how does it decide which recipes to cook at exactly the right moment? Your cells are not dumb factories running on autopilot. They're incredibly smart, self-regulating systems that constantly sense what's happening inside and outside the body. Stress levels, nutrient availability, inflammation, sleep quality, even how much exercise you did yesterday. Based on that real-time information, they decide which peptide recipes to read right now. This decision-making happens through two beautifully orchestrated steps, transcription and translation. Think of it as the cell's own high-tech printing press and assembly line working together in perfect coordination. Let's spend the next few minutes on transcription, the first step where the DNA recipe gets safely copied. Picture the DNA double helix sitting inside the nucleus like a priceless ancient book that never leaves the building. When the cell needs a particular peptide, a special enzyme called RNA polymerase moves in. It gently unzips a small section of the DNA right at the gene it needs, just like opening the book to the correct page. Then, RNA polymerase reads one strand of the DNA and builds a matching single-stranded messenger RNA molecule, mRNA for short. It's essentially photocopying the recipe onto a disposable sheet of paper. The mRNA is a perfect complementary copy of pairs with U, C with G, and so on. This mRNA copy is much smaller and more mobile than DNA. So once it's made and checked, it can exit the nucleus through tiny nuclear pores and travel out to the cytoplasm. But here's the first major regulation point, and where your daily life directly influences which peptides get made. Before RNA polymerase even starts copying, special proteins called transcription factors have to give the green light. Many of these transcription factors are peptides or small proteins themselves. They act like factory managers with master keys. Imagine the factory manager walking into the library, checking the current conditions on the factory floor, and then pointing at a specific recipe. Copy recipe number 47 for collagen repair peptides right now. Or, if the body's under chronic stress, the manager might say, hold off on those repair peptides and instead copy the inflammatory signaling ones. We're in survival mode today. These switches flip based on real signals. High cortisol, low magnesium or vitamin D, poor sleep, or positive inputs like intense exercise, high quality protein intake, or deep recovery. Every choice you make sends chemical messages that tell transcription factors which genes to activate or silence. So transcription is highly regulated. It's not automatic. The cell is constantly asking, do we need more repair peptides today, or should we prioritize survival signals? Once the mRNA copy is approved, it leaves the nucleus and heads to the next stage, translation, the actual building of the peptide chain. The mRNA docks onto a ribosome, the cell's protein-making machine, often described as a molecular factory or even a tiny robot. The ribosome reads the mRNA 3 letters at a time, each triplet codon calling for one specific amino acid. Then transfer RNA molecules, tRNA, act like delivery trucks. Each tRNA carries exactly the right amino acid matching the codon. The ribosome snaps the amino acids together one by one, forming a growing peptide chain. It's like an assembly line clicking Lego bricks into place with incredible speed and precision. When the ribosome reaches a stop codon, the chain is released. Some finished peptides stay inside the cell to do local jobs. Others get folded, modified, packaged into little vesicles, and secreted outside the cell to travel through blood or tissue fluid as messengers. And there's a second layer of regulation here too. Cells can speed up or slow down ribosomes depending on energy availability. They can destroy faulty mRNA before it's translated, or tag finished peptides for immediate use or quick degradation. This fine-tuning keeps everything efficient. All of this creates elegant feedback loops. One peptide can turn its own gene on or off, positive or negative feedback, keeping energy production, tissue repair, and inflammation in perfect dynamic balance. This is true cellular self-regulation. Here's the ageless tie-in. As we get older, this whole system becomes less efficient. Ribosomes slow down, more errors creep into the copying process, transcription factors become less responsive, and feedback loops get sloppy. The result? Fewer youthful repair peptides, more inflammatory ones, and a gradual decline in how well your body maintains itself. The good news is that many of these declines can be influenced by how you live. So, quick mental picture. DNA in the nucleus gets transcribed into mRNA. mRNA travels to the ribosome. tRNA delivers amino acids, and out comes a finished peptide, all under tight environmental control. Now the peptide is born. The real question is, what does it actually do inside the cell or throughout the body? Let's find out how these tiny messengers exert their powerful effects. Now the peptide is born. So, a precise chain of amino acids fresh from the ribosome. The real question is, what does it actually do? How does this tiny molecule tell a cell or an entire tissue what to do? Most peptides function as highly specific messengers. Think of them as text messages written in the language of life. They travel through blood, tissue fluid, or even stay inside the cell, looking for the right recipient. They work like keys that fit perfectly into specific locks called receptors. These receptors sit on the cell surface or sometimes deep inside the cell. When the right peptide key slides into its matching receptor lock, it triggers a cascade of events that can completely change how that cell behaves. Let me give you a couple of powerful examples. Take growth hormone releasing peptides or certain collagen-derived peptides. They often bind to G protein coupled receptors on the cell membrane. The moment they dock, the receptor changes shape and activates internal signaling molecules. Second messengers like CAMP. It's like flipping a domino. One small binding event sets off a whole chain reaction inside the cell. What's the result? The cell suddenly ramps up production of repair enzymes, increases collagen synthesis, reduces inflammatory signals, boosts mitochondrial energy production, or tells nearby cells to join the repair effort. In seconds to minutes, behavior changes from maintenance mode to active healing mode. Other peptides go even deeper. Some peptides actually travel all the way into the nucleus and act as transcription factors themselves. Once inside, they bind directly to specific stretches of DNA and turn entire networks of genes on or off. These are master controllers. They don't just tweak one thing. They orchestrate dozens or hundreds of genes at once. For instance, certain regulatory peptides, brachytherapy peptides, can activate genes involved in autophagy, the cell's recycling system that clears out damaged proteins. Others can suppress genes that drive chronic inflammation or push cells into senescence. The zombie cell state, where cells stop dividing but keep pumping out inflammatory signals that age the whole neighborhood. So peptides are doing two big jobs at once: short-term commands through surface receptors and signaling cascades. Long-term reprogramming by directly influencing which genes get read. Here's a simple analogy that makes it all click. Peptides are the text messages your cells send to each other, and even to their own DNA. Some texts say, "Hey, ramp up repair right now." Others say, "Turn down inflammation across the whole network." And the most powerful ones walk straight into the control room and rewrite the daily schedule. This is where the anti-aging magic really shines. When your peptide signaling stays youthful and balanced, stem cells remain active and ready to replace damaged tissue. Damaged proteins and organelles get cleared out efficiently through autophagy. Senescent zombie cells are kept in check or cleared before they can spread inflammation. The result is better skin elasticity, faster recovery from exercise, sharper mental function, and slower biological aging overall. But when peptide signaling gets disrupted by chronic stress, nutrient gaps, or simply the wear of time, these commands become weaker or distorted. Repair slows, inflammation simmers, stem cells go quiet, and senescent cells accumulate. That's when we start to look and feel older than our chronological age. So peptides aren't just passive building blocks. They're dynamic communicators that translate your genes into real-time action. But nothing lasts forever. Ibn Sassam. Even the most powerful text message eventually gets its job done. So what happens after the peptide delivers its message? How does the body clean up, recycle, and keep the system from getting overwhelmed? That's exactly where we're headed next. But nothing lasts forever. Even the most powerful peptide message eventually gets its job done. So what happens next? Most peptides are deliberately short-lived. They last only seconds to a few minutes inside the body. This isn't a flaw. It's brilliant design. It gives your cells precise, moment-to-moment control. Once the message is delivered, the peptide needs to disappear quickly so it doesn't keep signaling when it's no longer needed. Enter the molecular scissors, proteases. These specialized enzymes patrol the cell and bloodstream like cleanup crews. They recognize the used peptide and chop it into individual amino acids. Snip, 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 breaking the chain back down into its basic building blocks. Those freed amino acids don't go to waste. They're immediately recycled back into the cell's amino acid pool, ready to be used again for building brand new peptides or proteins. It's the ultimate circular economy happening inside every one of your cells. Zero waste, maximum efficiency. This recycling system keeps everything running smoothly and prevents the cell from running out of raw materials. Here's where aging enters the picture. As we get older, the body's clearance systems naturally slow down. Two key systems, the ubiquitin proteasome pathway, which tags and destroys specific damaged proteins, and autophagy, the cell's self-eating recycling process, become less efficient. The result? Peptide traffic jams. Old or damaged signaling molecules linger longer than they should. This creates chronic low-grade inflammation, often called inflammaging, the hidden driver behind many age-related issues like joint pain, brain fog, loss of skin elasticity, and slower recovery. When cleanup slows, the elegant peptide communication system gets noisy and confused. Signals that should have been turned off keep whispering in the background, keeping inflammation turned up and repair turned down. The good news is you're not powerless. Simple lifestyle choices powerfully upregulate these cleanup systems. Strategic fasting, regular exercise, especially resistance training and HIIT, quality deep sleep, and even cold exposure or heat therapy like saunas all boost autophagy and proteasome activity. When these cleanup crews work at full speed, peptides deliver their messages cleanly, get recycled efficiently, and the whole system stays sharp and youthful for much longer. So remember, it's not just about making more peptides, it's about making sure the old ones get cleared out so the new ones can do their job perfectly. We've now followed the entire journey from DNA recipe through transcription and translation to the peptide doing its work, and finally, its graceful exit and recycling. Next, we'll zoom out and look at how all of this connects to staying biologically young and what practical steps you can take to keep your peptide pipeline running at peak performance for decades to come. From the DNA blueprint in your genes, through the cell's self-regulating factory of transcription and translation, all the way to receptors, cellular commands, and elegant recycling, your body is running a non-stop peptide symphony that literally decides how young you stay, day after day, cell after cell. The more we understand this intricate biology, the more power we have to support it. Through smart nutrition, targeted lifestyle habits, and when appropriate and under professional medical guidance, emerging peptide therapies, we can help keep the entire pipeline running smoothly. Better repair, lower inflammation, and slower biological aging. If you want to go deeper, check the show notes. I've linked key studies on peptide signaling and longevity, plus simple, practical ways you can support your cellular factory starting today, no fancy equipment required. Stay curious, stay youthful, and take great care of the incredible orchestra happening inside you right now. See you next time on The Science of Ageless Living. I'm Dr. Ethan Hausman-Marquis.